We're almost all here. So, do take note of this important life lesson. Victorious warriors win first and then go to war, while the defeated warriors go to war first and then seek to win. The difference is planning, right? Plan ahead so that when the time comes and you actually do the task, you can just move forward and execute. Okay. So, back to math. Previously, we have been studying the rational functions. Okay. They're very nice and orderly, very logical thinkers, those rational functions. And we practiced some graphing. We looked at the zeros, okay, how to find the intercepts of both x and y. And that's going to give us half the picture. The rest of the picture comes mainly from the asymptotes. Okay, so what we need to look at now is how to find the asymptotes of a rational function from its equation. And it's actually rather simple. A lot of people like to think of it as this convoluted, complex thing of like, oh, has it got a horizontal one? Is it going to have a slant one? It's actually really simple. You just got to check two little numbers. That's it. Two numbers. You're going to compare and contrast two numbers out of that function. And that's going to tell you everything you need to know. What are those two numbers? They are the highest powers. When it comes to finding the asymptotes, start with checking the highest powers, the highest exponents on the numerator versus the denominator. Right? That's all you need to do. So for example, look at f of x here. F of x is equal to x cubed plus x squared plus x plus 1, all divided by x squared plus 2. There's a whole lot of extra nonsense on here that I don't need, I don't care about right now. I want the leading term, and I just need its exponent. So we're comparing 3 versus 2. Who wins? Which one is bigger? That's an easy question. You can write that. 3, very good, Fernando. The numerator wins. Yay, right? And confetti comes down. It wins the big prize. Okay. How about g of x? Check that your polynomials are listed in standard form on top and bottom. They are, so the highest one comes first. So I just need to compare 3 versus 3. Ooh, who wins? Anybody win? None. Nobody wins. Yeah, it's a tie. That can happen, right? That's okay. That tells us something. And then here, h of x, I've got x squared over x cubed. So which one wins? The denominator wins. Thank you, Leslie. All right. That's what you're going to check for. And what does this actually tell you about the graph? Well, it indicates what's going to happen as x approaches infinity. Remember our terms here, right? As x approaches infinity. When x gets really large, and now technically, yes, this also includes, oops, negative infinity. That is included there as well. But when it comes to the asymptotes, right, a horizontal asymptote, nice and flat, it goes to positive and negative equally. If you have a slant asymptote, just checking one direction, we'll know, okay, it also goes back the other way, okay? So as far as asymptotes is concerned, we really only have to think about half of the graph, and the rest will follow to match. So think about what happens as x approaches infinity. And remember, my mental trick for positive infinity is plug in 1,000,000. I have yet to see the textbook example for any math problem where plugging in 1,000,000 for x is not ridiculously close to the asymptote, okay? That's your end result. Unless one of the coefficients is itself in the millions, you could just plug in 1,000,000 and imagine what's going to happen. If the numerator wins, that is to say, you have several millions multiplied together on top, divided by 1,000,000, but fewer millions in the denominator. What happens there, right? Just think in terms of x's. The only thing that's important as x approaches infinity is the leading coefficient, okay? 1,000,000 cubed plus even 1,000,000 squared, okay? 1,000,000 squared is nothing. That's bupkis. That does not affect the graph almost whatsoever when you get way out there towards positive infinity. So what we're saying here is, what is 1,000,000 cubed divided by 1,000,000 squared? Remember your rules of exponents. Right? Those extras cancel out, reduce, and you're left with just the one value there. Pretty nice. So, if the numerator wins, what's going to happen to the function? The function is going to approach infinity, way out there somewhere, in one fashion or another. I will put a disclaimer on here. Hold on, give yourself a little more space. Positive or negative. Because, of course, if we have a negative coefficient on the front, that flips the whole thing upside down and it zips down towards negative infinity. But we can be a little bit more specific than that. Take a look at function j. Who wins in function j, numerator or denominator? Numerator, clearly, right? X to the 6th power. In fact, the numerator wins by a lot, okay? 6 minus 2 is 4. The numerator wins 4 times over. If the numerator wins by a lot, that is to say more than 1, so let's go, I'll go into pink here, right? Stop moving around when I'm trying to write the thing. Okay, if wins by greater than 1, then the function takes off. Like, there's another e there, like a polynomial. All right? Way out here in the edges, this function here is going to do all of its business, and then eventually, that's not even good. Let's see, do all of its business and then take off like that. Okay, you're going to get this exponential seeming growth. It's not actually exponential, but right, it's going to curve up infinitely, just like up the edges of a parabola. Okay? If it only wins by 1, then the function continues linearly. It won, the numerator wins, but not by a lot. Exactly 1 power over. Okay? So when you reduce them, if there's only one power of x left in the top, well, then it's going to look exactly like a single power of x looks like. That is to say, a line, a flat, straight line that's not horizontal. And this is the slant asymptote. Okay? And it's going to be equal to your lead coefficients plus whatever constant on top, right? You have a shift there. And I foolishly didn't put any, did I? Let me check which one. H was my example there. So our lead coefficient, which one was that? G. No. Who won by 1? F. F1 wins by 1, right? 3 versus 2. Numerator wins by 1. So then this is going to have a slant asymptote at y equals, well, what's the coefficient? This is 1. This is 1. 1 over 1 is 1. So it's just 1x plus the constant there, plus 1. Pretty boring slant asymptote. That happens, right? If this was 3, it would be 3x. If this bottom coefficient was 2, this would be 3/2 x plus 1. See what we're doing there? You reduce out all the extra stuff. It dies off when x approaches infinity. And the only thing left is this guy, this number here, and the constant, which is your y-intercept of the slant asymptote. Because you're probably going to have to plot, that is to say, put it on your graph, the slant asymptote, just as a dashed line. Okay, let me go back to that text on screen. Any questions there? That is the most complicated outcome. If the numerator wins, you've got to do a second check. Wait. Wins by how much? Because if it only wins by 1 power, you have the slant, the most complicated option. If it wins by more than 1 power, remember that at x equals 1,000,000, it's always going to come down to, it will resemble the reduced function of the lead coefficients, or the leading terms. You just reduce those leading terms, and that's what it will look like in the end. So if that looks like a line, it looks like a line. If it looks like a parabola at the end, it'll just take off like a parabola at the end, or a cubic, or a quartic, whatever. Okay, no questions coming up there. So let's look at the other options. If the denominator wins, okay, that is to say, you are dividing by many more millions than you are multiplying by. Dividing anything by many millions is going to leave you with, well, not much. Literally, try to divide up a pie among 1,000,000 people and see how much you have left to eat, okay? It's basically nothing, right? Pathetic. If the denominator wins, it's going to go to 0. The function will return back to approach 0, and so you get that horizontal asymptote at 0. Right? This is horizontal asymptote at y equals 0. There's flat lines. Now, if they tie, like they did in, what was that, g of x, right? 3 versus 3. then nobody wins. The function neither takes off higher, nor is it dropped down to 0. It stays pretty steady. Like, okay, multiply by 1,000,000, but then you divide by 1,000,000 again. For every another 1,000,000 you multiply by, we're dividing by another 1,000,000 again. So it changes nothing. So the only thing left is whatever we started with, the very first numbers, that is to say, the coefficients on there. So once again, it's the ratio of the lead coefficients, except this time composing a horizontal asymptote. So our function approaches, I'll just call it A over B, some ratio of the lead coefficients in your numerator versus denominator. So again, a horizontal asymptote at y equals A over B, where A leads the numerator and B leads the denominator. Clearly, I should have left myself a little more room. So in the case of g of x up there, we had a 2 up top, a 1 on the bottom. So the g of x function has a horizontal asymptote at y equals 2. Way out on the extreme ends. It's going to flatline and approach, but not 0, bumped up to 2. Any questions there? Okay, that's it. So now you know, where's the horizontal, if anywhere, or is it slanted? It's not that bad. Now we just need the big ones, the ones that make the whole function, rational function, like really pop out on the picture, the vertical asymptotes. So step 2, after you found the horizontal or slant, find the verticals. And that's as easy as checking for the excluded values. The one thing you're never allowed to do in math, divide by 0. What would cause you to divide by 0? Right? Wherever that would happen, well, it's not allowed to happen. So those are your excluded values. We've been practicing calculating them already. But there's a catch. Okay? Not all of them lead to asymptotes. Okay? There is more than one type of discontinuity. We studied those before. Anyone remember? You have asymptotes, the non-removable discontinuity, or you could have anyone in chat? What's the other option there? Well, I gave it away with the other name. Instead of a non-removable discontinuity, it would be a what?
Removable one.
Removable discontinuity. Very good. Anyone know another name for removable discontinuity? Something that we could take out of the function and just ignore it. Just kind of like plug it up and pretend it's not there and just skip right over that spot.
Coefficients.
Coefficient, you can just plug up and ignore the coefficients? No. A hole. We're looking for a hole. If your excluded value is also a 0, that is to say, it is a factor or it causes the numerator and the denominator to equal 0, then it is a removable discontinuity. which is fancy talk for a hole. Why is it called removable? Well, recall, if we were to factor these guys, we could have something like x minus 2x plus 2 divided by x minus 2. Real simple example. Hey, look, I've got the same thing on the top and the bottom. I'm going to reduce them, right? And so you cross those guys out. You reduce it, and you just get y equals x plus 2. If this starts as a rational function, right? It's a ratio of two polynomials, one divided by the other. But it reduces to just a linear. So as before, hey, what if I multiplied these out? I'd have x squared and single x squared divided by x. The numerator wins the power war, but by exactly 1. So, as we said earlier, it's going to have a slant asymptote. The whole thing rides right on the asymptote, because it's just a line, but with a hole in it, at x equals positive 2, right? The thing you lose if you reduce this and write the function this way is that bit of information. Wait. Originally, I was not allowed to let x equal to 2. But I removed the discontinuity and said, we'll draw over it anyways. We just should ideally highlight right there and say, hey, wait, there's a hole here at x equals 2. Right? That's not so bad. Those are things you got to check for anyways, right? So I always like to start looking for asymptotes. Start with that list. Start with the discontinuity list, the excluded values. Then find the zeros from the numerator and compare lists. Anything that appears on both lists, it's a hole. Okay, write that in the holes category. Anything that's only in the denominators list, that's a vertical asymptote. Write that in a separate category. And anything that's only on the numerators list, that is a true zero of the function. Remember earlier we said possible zeros. We only found the possible zeros before because we only checked the numerator. Right? If they're on both lists, it's not a zero. This function is not crossing through the x-axis at x equals positive 2. Right? Because it's reduced form, plug in positive 2 here, y equals 4. It looks like it's going to appear at 2 comma 4, except there's actually a hole there. So it's going to all but be at 2 comma 4. Right? That's not a zero of the function. See the difference there?
We can get some pooch? Fuck it.
Okay. Fernando? We can hear that. Thank you. All right. So the only possibility left, if it is not also a zero, then your excluded value becomes the vertical asymptote. So when you have y equals 1 over x minus 2. X cannot equal positive 2. Therefore, we have a vertical asymptote at x equals 2, which means on your graph, instead of having your 1, 2, you go dotted line right there. And now the graph can do its thing. All right, questions there? Not too shabby, eh? All right, then, as promised, we are continuing to work with the very same functions as before, which were on, not the geometry section. No, that's not the one. Intercepts, that's the one, right? You guys did this last week, so very same functions are on your worksheet for this week, except the instructions are different. Now we're looking for list all the asymptotes for all of these functions. And guess what we're going to do next? Put it all together, and then you can start drawing these guys. Okay? So one step at a time. Just find me all of the asymptotes for these functions for today. Okay. Any last minute questions? What we're doing? All right, then I will leave you to it.